In this lecture, we shall be studying Maxwell's inductance capacitance bridge. Popularly, this bridge is also called Maxwell-Venn bridge. This lecture has been prepared by Dr. R.S. Tare and Professor Saurabh Jain. The objectives of this lecture are to enlist the use of Maxwell's inductance capacitance bridge, to understand the circuit layout of Maxwell's inductance capacitance bridge, to derive the balance equations for the Maxwell's inductance capacitance bridge, to draw the Phasor diagram for Maxwell's inductance capacitance bridge, and finally to list the advantages and limitations of this bridge. Let us first answer the question for what Maxwell's inductance capacitance bridge is used. Let us first answer the question for what Maxwell's inductance capacitance bridge is used. We frequently encounter applications of inductance in power systems, power electronics, electrical machines, and other fields of electrical engineering and electronics and communication engineering. When a practical inductance is fabricated, it is always associated with some resistance as a built-in feature due to resistance of the conductor used for making the inductance, and because of losses taking place in magnetic material used in the construction of inductance. Thus, we need an instrument to measure the inductance of a coil along with the equivalent resistance of this coil. Maxwell's inductance capacitance bridge measures the unknown inductance and the equivalent resistance of the coil in terms of standard variable capacitance and standard variable resistance. This figure shows the circuit layout of Maxwell's inductance capacitance bridge. This bridge is characterized by arm 1 having unknown inductance L1 to be measured with its equivalent unknown resistance R1. Arm 2 having a standard resistance R2. Arm 3 having a standard resistance R3. Arm 4 having a standard resistance R4 connected in parallel with capacitor C4. Both R4 and C4 are known. E is the applied AC excitation of frequency omega. E1, E2, E3 and E4 are the 4 arm voltage phasors. D is the AC detector. A, B, C and D are the 4 vertices of the bridge. I1, I2, I3 and I4 are the 4 arm current phasors. Later, we will justify why we prefer to keep capacitor C4 and resistor R4 as standard variable elements. Now, we will derive the balance equations for this bridge. Since in this bridge all the 4 arms are quite distinct, therefore we can use the equation Z1 into Z4 equal to Z2 into Z3. Let us define the 4 arm impedances for this bridge. Z1 equal to R1 plus J omega L1. Z2 equal to R2. Z3 equal to R3 and Z4 equal to parallel combination of R4 and 1 upon J omega C4. This leads to Z4 equal to R4 into 1 upon J omega C4 divided by R4 plus 1 upon J omega C4. After a bit of simplification, Z4 equal to R4 upon 1 plus j omega C4 R4. Let us substitute the expressions for Z1, Z2, Z3 and Z4 in the equation Z1, Z4 equal to Z2, Z3. After substitution, we get R1 plus j omega L1 multiplied by R4 upon 1 plus j omega C4 R4 equal to R2 into R3. After simplification, we get R1 into R4 plus j omega L1 R4 equal to R2 R3 plus j omega R2 R3 R4 C4. After separating above equation in real and imaginary parts, we get R1 R4 equal to R2 into R3. From this equation, we get the expression for unknown resistance R1 as R1 equal to R3 upon R4 into R2. Equating the imaginary parts, we get omega L1 R4 equal to omega R2 R3 R4 C4. From this equation, we can write an expression for unknown inductance L1 as L1 equal to R2 R3 C4. Now we will try to obtain an expression for Q factor of the coil. The Q factor of a coil is given by Q equal to omega L1 upon R1 for the given frequency omega. Let us make substitution for the values of L1 and R1 in the form of expressions we have already obtained. Q equal to omega R2 R3 C4 divided by R3 upon R4 multiplied by R2. This yields a simple expression for Q factor of the coil. Q equal to omega C4 R4 for the given frequency of excitation omega. Let us quickly make some important observations on the balance equations of this bridge. R4 appears in first equation but not in the second equation. Capacitor C4 appears in second equation but not in the first equation. Therefore, for ensuring fast convergence of this bridge, we must select C4 and R4 as the standard variable elements. The balance equations for this bridge do not contain frequency term omega. Therefore, very stable frequency AC source of nearly sinusoidal wave shape is not required. Now we will make an attempt for drawing the phasor diagram for Maxwell's inductance capacitance bridge. Important observations in this bridge are: under balance condition, current I1 equal to I3 and current I2 equal to I4. Further, the voltage drop VBC equal to voltage drop VDC, both in phases and in magnitudes. There are two paths for currents flowing between points A and C. Current I1 through R1, L1, R3 and current I2 through R2 and parallel combination of R4 and C4. The path of current I1 is inductive in nature because of the presence of inductance L1. Therefore, supply E will lead current I1 by some angle. Path adopted by I2 is capacitive in nature because of the presence of capacitance C4. Therefore, supply E will lag behind I2 by some angle. Let us start drawing the phasor diagram now. Phasor current I1 is taken as a reference and this has been shown in the phasor diagram shown below. The current I1 passing through resistance R1 will create a voltage drop in phase with I1 and having a magnitude equal to I1 into R1. Current I1 passing through the inductive reactance j omega L1 will create a voltage drop equal to I1 into j omega L1, leading I1 by 90 degrees. This has been shown in the phasor diagram. From the circuit diagram of the bridge, it becomes evident the phasor sum of I1 into R1 and I1 into j omega L1 will be the branch voltage VAB. This has been shown by the red colored phasor VAB in the phasor diagram. When current I1 passes through R3, it will create a voltage drop equal to I1 into R3 in phase with I1. So from point B, we will draw a line parallel to I1 having a length equal to I1 into R3. The tip of this line will end in point C. So BC will represent the voltage across branch BC as VBC. The violet color phasor VAC is the total supply voltage E. In the next attempt, we will try to estimate the phasor of current I2. When I2 flows through R2, it will create a voltage drop equal to I2 R2 in phase with I2. We know in this bridge the voltage drop VAB must be equal to voltage drop VAD. Therefore, phase of VAD must be same as phase of VAB, and the phase of I2 is same as phase of VAD. Therefore, the current I2 will be in phase with VAB. We have drawn a green colored line representing I2 in phase with VAB. The voltage drop VAD is I2 into R2 and VAD is same as VAB. That is, point D and B are overlapping over each other. So we will draw a line along VAB having the same length as VAB, that is in phase with I2, representing the voltage drop I2 into R2. Point B and D must overlap over each other. The current I2, when it reaches node D, it gets divided into two parallel paths, IR4 along resistance R4 and IC4 along capacitance C4. The voltage drop created by IR4 passing through R4 is IR4 into R4. This voltage drop must be equal in magnitude and in phase with the voltage drop VBC, that is I1 into R3, which is in phase with I1. Therefore, phase of IR4 and phase of I1 must be same. Alternatively, the current IC4 passing through C4 will create a voltage drop equal to IC4 into 1 upon j omega C4, lagging behind current IC4 by 90 degrees. And this must be same as I1 into R3. Therefore, phase of IC4 must lead the phase of I1 by 90 degrees. In a nutshell, current I2 has to be split in two rectangular components, one along I1, that will be IR4, and another component leading I1 by 90 degrees, that is IC4. IR4 and IC4 have been shown in the phasor diagram. A voltage drop equal to IR4 into R4 along VBC in magnitude and in phase is shown in this diagram, which is parallel to IR4. Another phasor along VBC is IC4 into 1 upon j omega C4 is also shown. The voltage drop IC4 into 1 upon j omega C4 lags behind IC4 by 90 degrees and it is equal in magnitude equal to VBC. Let us now discuss the advantages of Maxwell's inductance capacitance bridge. The first most obvious advantage is this bridge is very simple in construction. The next advantage is the balance equations are independent of variable elements R4 and C4. Therefore, the convergence of this bridge is very fast provided we select R4 and C4 as variable elements. This bridge is quite suitable for low Q coils. The balance equations do not have frequency term omega. Therefore, very stable frequency excitation having a nearly sinusoidal wave shape is not required. Let us quickly discuss the disadvantages of Maxwell's inductance capacitance bridge. When this bridge is used for the measurement of inductance of high Q coils, the value of R4 becomes very high. Getting a standard non-inductive resistance of high value is pretty expensive. Therefore, this bridge is not suitable for the measurement of inductance of high Q coils. Now, let us summarize this lecture. In this lecture, we have learned following: the use of Maxwell's inductance capacitance bridge, the circuit layout of Maxwell's inductance capacitance bridge. We have learned the derivation of the balance equations for the Maxwell's inductance capacitance bridge. We have learned how to draw the Phasor diagram for Maxwell's inductance capacitance bridge. We have learned various advantages and disadvantages of the Maxwell's inductance capacitance bridge.